Hello everyone, my name is Olcan Canbek. I work for GCP Applied Technologies. I'm a colleague of Nathan, and so I'm here to present the work my PhD advisor Kim Kurtis at Georgia Tech led together with my former PI, actually, with Neville Washburn. So the authors, they couldn't be here today, unfortunately, so Kim asked me if I can present it. I said, yes, sure, of course, but I won't be able to answer obviously difficult questions. So this work is the Bayesian machine learning for modeling and design of UHPC, ultra-high performance concrete. So the inputs in machine learning, they are also called features, as you would know. And it's really important to find good features that are informative and interpretable. So it's and that's essentially called also called applied machine learning in Andrew's words, as you can see on the right. And for cement and concrete, it's typically in literature you would see a lot of models incorporating like the compositional features, and the authors at this work, they will argue that it's really important to engineer these features based on composition to get more generalizable and accurate model. So an example, so there's a very famous data set, a concrete strength data set consisting of roughly 1,000 data points. And there are papers trying to, build predictive models using this data set. There are multiple papers out there. And the inputs for this data set are water to cement ratio, the fly ash coarse aggregate, for example, like the water reducing, like the amount of water reducing agent, the dosage, and the air. So these are all these features that I also, some of them I didn't count here. They are compositional based. And recently, there was a paper published in CCR from UCLA showing how a machine learning model can predict concrete strength using these compositional variables, but the accuracy was moderate. And the authors for this work, they were wondering, okay, what if, what can we do if we have a small data set, like not 1,000 data points, but more like 50 or to 100 orders of magnitude lower than what you would typically see in machine learning models, using latent variables, so-called latent variables in their words, that are engineered, that are designed based on compositional variables. So these hidden variables or latent variables, they are again based on composition, but they inform the model in a better way because these are more like physics-based equations. They can be physics-based equations, and they tend to explain your model, your predictions, for example, based on like particle packing, rather than just saying, okay, this is, for example, median particle diameter of individual features. So they bring all these features together to yield more accuracy and more generalizable model. So the goal in this work is, and in general in the machine learning models of the cementitious systems, is, of course, the accurate predictions of many things like workability, set time, strength development, durability. But in our field, we typically don't have like large data sets. So, for example, in bioengineering, those folks they work with thousands of data points. We usually don't get in our field, so we have to find ways to build interpretable and accurate models with like small data sets. And the key for that is the feature engineering, essentially. As something maybe like not very common in literature, you would see in our field for the machine learning models are the the uncertainty estimates. So we would always see these Pareto plots. X-axis is the actual value, or like the predicted value. Y-axis is the other one. So we always report like the R-squares, but we don't usually look at like how confident we are in our predictions. So which is like the uncertainty estimate, which is something the authors demonstrated this work using Bayesian models. So I'm sure most of you are familiar with Bayes' theorem. Like unlike like frequentist statistics, in Bayes' theorem, you update your estimate based on the evidence you gain essentially. And in machine learning models based on this theorem, you have a prior distribution representing like the expectation of the range of your results without observing anything. So you generate multiple functions, and in posterior distribution you update your estimates based on given data, and you can create the confidence intervals as well, which you can see in these figures on the right. So at this work, the authors they exploited the Bayesian models, two different Bayesian models, to predict compressive strength of UHPC. So UHPC, just briefly, it gives really high compressive strength, like more than 150 megapascal. Typically, it has low water-to-cement ratio. But because of this, you have to use superplasticizer. So it's challenging actually to design like a really good UHPC, and also it's hard to model, obviously. So the authors they embarked on engineering different features based on composition of UHPC. So in this figure on the top, you will see actually like a schematic showing their modeling approach. So they demonstrate here like the compositional variables in their bottom layer. So it is like the amount of cement, the fines percentage, superplasticizer, supplementary cementitious ratio, water content, and fiber, I think volumetric amount of fibers included in. So these are the compositions, the compositional variables, excuse me. And they constructed a middle layer, which are different features, but based on this compositional variables. For example, they calculated particle packing based on Delarore's compressible packing model. And they represented particle packing with packing index parameter that's calculated based on particle diameters and the solus content. The other variable is water film thickness. That's like the excess water lubricating the cement particles. The higher the water film thickness, the better the workability you typically have, but less strength. Fiber relation, it's an empirical equation relating fiber content to compressive strength that they got from literature. Equivalent cement, that's like a proxy for the reactivity of their cementitious binders. So there's an equation calculating that, which takes into account the heat contribution of the SEMs included in the cementitious binders, for example. Also the cement itself. And finally, they also used superplasticizer cement and water content in the middle layer as well, because they were not, they were really important features they realized and were not really represented by the other bottom layer parameters. And they built different models based on, for example, only the composition. So they relating compositional variables to strength plus middle layer parameters, the engineered features, to strength, and they compared these, as you will see in the next slides. Where the data came from, so the authors looked at literature. There were 4 papers where they got the data from. totaling to, I believe, roughly like 100 samples. And as you can see, they vary in SCM, fine aggregate content and features, as well as like the fibers. And they built, again, Bayesian-based machine learning models where they randomly split their data set into training and test sets by 80 to 20% respectively, if I'm not mistaken. So the first model I will talk about here is something called Bayesian ridge regression. So I'll actually try to explain this. So for example, the difference between ridge regression and linear regression is that you have a regularization parameter in ridge regression, which kind of adjusts your regression coefficients while looking at, like the output. So there's an hyperparameter. When you include Bayesian in that, so now you're not, predicting one single output or target variable. Instead, you're constructing distributions where you can kind of estimate like the uncertainty of your target variable based on the variance you get from these distributions. When it's ensemble Bayesian ridge regression, so now it's like more complex. Now you have multiple Bayesian-based ridge regression models, kind of like they're each voting your target variable. So it's kind of like a more generalizable and helps improve your accuracy as well. And you get, again, uncertainty estimates. That's what they used here. And so showing results from both composition model and latent model. So the composition model means inputs are only compositional variables. Latent model means, as I showed in this previous slide, your inputs are from coming from the bottom layer. Surprisingly for me, not I guess for them maybe, the latent variable model actually gave a lower root mean squared error a higher error on the testing set versus composition-based models. The difference is not much, but composition-based model did better. But actually, when you look at like the uncertainty estimates, which they retrieved through calculating miscalibration area, the authors realized that, okay, my composition-based model has a higher miscalibration area compared to the latent-based model, which implies, okay, my composition-based models is very actually overconfident in my estimate. So maybe you can realize this. Maybe you can kind of understand this through like the confidence interval analogy. So assume, for example, you have a really wide range of confidence interval in your predictions. So you're not really confident that like your single point estimate is giving you actually like a good estimate. Okay, so just to wrap up here, so composition-based models has a lower error, but it's more uncertain. Suggests that, as the last sentence puts out here, the latent model would be better in terms of generalizability, meaning that you can extend the latent-based models to predict strength of data that was not included in your entire data set. That's the hypothesis. And when the authors tested this hypothesis in a validation set, they got from another study that where the inputs are was not in the range of, for example, what they had in their whole data set. For example, the sand used in the validation set had a much higher particle size. So when they tested the different models, composition-based and latent-based models, they realized that in validation set, latent-based model did better this time, kind of confirming their hypothesis based on the uncertainty estimates. So I guess one takeaway from the study is that don't just look at your error metric, your root mean squared error, while comparing different models you built. Also look at your uncertainty estimate to understand which model you built will do better in a different data set that you may have. In conclusion, even small data sets on complex systems can be modeled, using machine learning techniques, and latent variables, which are again the engineered features based on the composition, can be really powerful to achieve high accuracy. And to acknowledge, NSF, I believe, funded this study, and Covestra, BASF, Imerys, Argos, and ARPA-E were the other institutions and companies supported this study, along with many grad students at that time, including myself, were part of this study. So thank you for listening. If I know the answer, I can answer the questions. Otherwise, I can connect you with the authors.